I propose that there is one physical sun and moon, in that each observer, every soul or consciousness, experiences a personalized projection of these celestial bodies. Now, this has been modeled before, but only with one observer. And this confused people because they thought light bended and they didn't really understand how this model works. So, what I'm focusing on now is having multiple observers and also explaining how this concept works under simulation theory, is how I believe this world works. That's how this projection works. For example, when we're inside, when I'm an observer right now in this model, when I look up, I should not be able to see the actual sun and moon on the firmament. All we see is the celestial sphere. I don't know why. That's just how creation works. And it seems that the pole is adjusted about 1 degree for every 60 miles from the North Pole. So you can see here how it's about 17 degrees from the horizon, and that's because my latitude is 17 degrees from the equator. This person is like in Mexico, that's about Belize. So yeah, it's roughly about 17 latitude, so then you're pointing up, and as you get closer to the North Pole, the celestial pole points straight up. But what I'm trying to focus on in this model is real life, actual equations, where stuff is, and making it map up to astronomy software as well. So there's something called declination. So let me find, this is Stellarium, anyone can use this software. But right now, the sun has a declination of 18 degrees. What that means is, from the celestial North Pole, it's 18 degrees from the equator. That's that line right there on the screen where it says 20 degrees. So where is that actually on the firmament? We can see the same celestial sphere here, but where other people haven't really taken it is now putting this into coordinates on the firmament with the height and everything. So 20 degrees? Yeah, 18 degrees. So if I was to now adjust this here, seeing the top left corner, it's at 19 declination. That's this up here in the top left. That is where this would be on the firmament. So halfway, the middle point of the firmament, let me go here. So the middle spot of the firmament, that is 0 degrees. And as I wanted to go to 20 degrees, that would be right up about there on the firmament. Does that make sense? So 0, 20, 40, and you go all the way up here as well. So if the highest up would be 90 degrees, that's that little tip of the pole. So 0 to 90 degrees. For example, the moon. Where's the moon right now? Oh, it also it's actually right by the sun, just at a different position, so that won't really map out well. But I can put it right beside it as well, though. So let's go to the moon and put it right beside it. So the moon has a declination of about 28. Let's put it actually right beside it. Slightly off. And this is 1 pixel for every 100 kilometers. This is the scale. So as I was showing you over here, this is the equation for how I believe the dome firmament to work. That's this up here in the top left. Now you see the D value, that's 69 degrees on how our vision works. You can measure that yourself. And then V is how many degrees we have until our celestial sphere completely rotates. So no matter what model you believe in, we have an equator, and you have 90 degrees above that and below that. So these are just values that anyone can use, and is quite objective. Now, where this gets interesting, though, is because we can start doing equations for that. So if I am at 0 right under the firmament, the highest point up is now 6,216 kilometers. We know that because it's plotted, and then consequently we can adjust this position. So now I am 4,000 kilometers out. That means the firmament is now 5,500 kilometers above me. So using these formulas that I calculated here, that is what I placed into this model. So you see here how we now know the height of the sun. Right now the sun has a height of 4,300 kilometers and the moon a little bit. And you can see as I adjust its declination, which is the value that is used in astronomy, the height of the sun changes. So at the very top of the dome, we get that 6,200 kilometers. And then as you go down, the height drops down, 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 down. We have a height of 400 kilometers right now. This sun is now 400 kilometers above the Earth. Now in real life, it doesn't actually go that low. I'm just experimenting now with the declination of the sun. I've been plotting it out here, and it seems to go from negative 20 degrees up to about 20 degrees. So let me just show you what that would look like. Where is negative 20 degrees? Oh, and I got these backwards actually. My negative sign's wrong. Okay, so this is 22 degrees of declination, and then we're going down to 20 degrees. So that would mean the sun is really orbiting this right here. Physically, the sun's never actually at the North Pole or the South Pole. It hangs out in the middle as it does its orbit. Now, the moon's something completely else. I don't know about that. But here, let me turn on the sun, just so you get an idea. Let me put the moon somewhere else, just so you can get out of the way. So this is how I believe the sun does its orbits. It'd be going up and down throughout the year, like that. And the most important thing here is that we're using real math and real observations. Everything is based off this model. The sun and moon are physically on this model now, and as it moves, the coordinates you see are adjusted here as well. Everything's being adjusted. The math is explained very well. Everything's there. It's really, really good. And then these two observers are the important things. We want to be able to go into here and also have this move. So that's what I'm working on now. But it's come a long way.